You ever Google your car problem and get nothing but crickets? Literal silence. Nobody has the answer, or if they had it, they ghosted the rest of us. We've all been there, professional techs too. We lean on Google more than our own repair manuals. All data, dealer portals, workshop subscriptions, they help most of the time, but sometimes the only manual is a oil-stained folder from a 1980s offshore powerboat team with a note scribbled on a napkin from an Italian restaurant. And yes, it's in Italian. So what do you do when nothing seems available? No part support, no service bulletins, no form posts. You got to go to the fundamentals: air, fuel, spark, instrumentation, logic. And today we're proving that on a 12-cylinder, 6-carb, 700 horsepower Lamborghini SUV. A literal boat motor stuffed into a road vehicle. Not a flex, not a museum piece, a practical lesson in how to diagnose and fix something when the internet goes silent. Keller, our quiet, deadly accurate shop tech, handles the wrench work, and you're getting real ASMR, wrench time, click-clack, no stylized editing, just craftsmanship. But before we dive in, comment below. What's the weirdest Google can't help repair that you've faced? Worst ghosted issue you've had to chase? We're genuinely curious, and hey, hit subscribe and like while you're at it. More reach means more insane projects like this to put on the channel. All right, so quick refresher for anyone following along, and for those who just want a reminder of how bonkers this project really was. Now, we've already covered this LM002 in 2 videos, but here's the gist. This is one of roughly 300 ever made even more Lamborghini by taking the Countach engine out and dropping in a 9.3-liter Lambo Marine V12 fed by 6 Weber DNCF 40 carburetors, a 76-gallon fuel tank, and a frame and suspension built for desert racing. Heavy, absurd, and brilliantly over the top in a way that makes you shake your head and grin at the same time. Now, in our first video, we inspected it, the oddities, the specs, everything, just to set the stage and get familiar with how unique this car really is and how wild the work already done has been. Now, the second video tackled the immediate showstopper, the cooling system. The previous swap had ran on boat logic, constant seawater flow, which on the road is basically a 10-minute time bomb. So we rethought the flow paths, relocated the pump, added a thermostat and bypass, fabricated a new expansion tank, mopped up an external electric pump for testing, and stabilized the system. 45 minutes at idle, steady around 190. That big dam was closed. But with the cooling stable, the car started showing its true personality. Mid-throttle hesitation, popping through the carbs, and occasional stalls and electric quirks that only really appeared under load. So if you haven't seen the first 2 videos yet, now's a good time because they're basically going to be the foundation for everything that you're going to watch going forward. Now, when you're flying blind with 0 documentation, welcome to our life on the LM002. Now, it starts to make sense why nothing's online. These Lambo Marine V12s weren't engines you could just download a PDF for. They were special order. If you need to ask, you can't afford it kind of deals. Either you were a tech yourself or you had a yacht or race team mechanic on staff. The manuals came with the engine, not posted online, and even if someone wanted to share it, the market's so tiny it probably wouldn't have paid for the paper it was printed on. That's why when you're stuck in this situation, there are rules that you gotta live by. Confirm the basics: air, fuel, spark, instrument everything. Fix the big dam first and change one variable at a time. Guessing's okay, but be prepared to pay, and no shortcuts, just fundamentals and measured problem solving. And in this video, you're gonna see a lot of Keller for good reason. Now, while I contributed to planning, diagnostics, and overall direction, it honestly pales in comparison to the talent, time, and effort Keller poured into executing, refining, and improving basically every step. From cooling to fuel, carbs to ignition, nearly everything running smoothly on this LM002 comes down to him. And I may have been the idea guy, but Keller is the one who made it happen. And for the next 30 minutes, that's gonna be your mental model. Carburetors are delicate little metallic divas, and on the multi-carb setup, they don't just sit there, they kind of talk to each other through airflow and pressure balance. The LM002's 6 Webers aren't really an exception. One carb out of sync, one regulator misbehaving, and suddenly half the engine's starving while the other half floods. Drama ensues. But key numbers matter here. These carbs like 5 to 6 PSI at the rail for smooth operation. Not random. If you're too high, you'll overflow the floats, puddle fuel, and flood the bowls. Too low and under transient load, the jets go lean, tip and pops, stumbles, hesitation. Carb-fed engines are volume sensitive. The pump has to maintain a steady flow at that pressure across all of the 6 carbs, and the regulators have to hold it steady. So here, the first check was to have Keller check the pressure. So we ran a gauge in between the pump and regulators, and what we saw was basically roller coasting swings from 0.5 to 4 PSI. And that explains why the carbs were acting like they had split personalities. The regulators themselves were a mess. The springs were backed out, and maybe the screws vibrated loose. The hardware was ragged and mangled. But a regulator without spring tension can't hold pressure. It basically leaks and fluctuates under load. So we had to tear them down, rebuild them, and get them properly functioning. That brought the pressure to a steady 1.5, better than 0.5, but still nowhere near big enough for 6 carb throats on a big V12. Next, the pump. Mechanical, cam, or lifter driven pumps are simple, but the volume is RPM dependent. Under high demand, they're limited. Electronic pumps, on the other hand, they'll let you dial in the flow, and they're basically a steady pressure solution. This engine needed volume, so we installed a Mr. Gasket 95P, no nonsense 95 gallon per hour inline electric pump, the kind you'd slap on a big block or Marine V8, and with the correct feed and return lines, pressure stabilized to that 5 or 6 PSI across idle and stimulated load. The immediate result was that the tip-in popping disappeared and the intermittent lean conditions basically dropped. The carbs are finally behaving. Takeaways for anyone trying this at home: start with an accurate inline fuel pressure gauge. You got to know your window, and if your regulator springs are loose, rebuild them before even touching the carbs. If pressure is still unstable, step up pump capacity. Flow-rated pumps, not the tiny donor unit. And when upgrading, match your lines and filters. A starved fuel feed line renders basically any pump useless. The bottom line, fuel pressure that behaves like a yo-yo equals an engine that behaves like a drama queen. Fix that pressure first and you'll cut out half the guessing. Get that right and the rest of the carbs, the sync, the ignition, it'll start to make sense. Now we get to the carbs. 6 Weber DNCF 40s, arranged as a pair per 2 cylinders. Each DNCF 40 is essentially a double-barreled progressive downdraft carb. So if you set them up right, they're brilliant for performance. But if you set them up wrong or leave them dirty, nightmare. Now, the fewer moving parts between your brain and the engine, the more brutally honest these carbs become. So the symptom was popping, and backfire, especially during mid-throttle. This is classic transient mixture issues, usually accelerator pump problems or float level discrepancies. On inspection, 3 of the 6 accelerator pumps were clogged, and that meant that on hard tip-in, half the engine got a proper squirt and half didn't. The result was lean, pop, and a lot of drama. We tore down each carb, inspected the accelerator pump diaphragms, and cleaned the passages and replaced the worn needles and seats where needed. Float levels were another surprise. Several were low, and a low float equals starved main jets and emulsification of the circuits. Even a tiny float discrepancy on this engine where each carb feeds 2 cylinders can turn into a very visible drivability problem. Now, we measured everything against Weber spec, reset the floats, verified bowl sealing, and pressure tested the bowls.
So what I'm checking now is the float level of the fuel bowl. This will allow fuel into your bowl of the carburetor. And these all seem to have sagged down too low. So I'm checking the height here against the mount of this top head or air horn, whatever you want to call it. Get it a little bit higher, I just need to bend this tab here. A small bend here will make a big change in your level. So I'm just going to go through all these floats, check them, make sure they're at the right level.
Once that was set, we could finally get to the main jets, and almost all of them needed cleaning too. Now, jets can look fine on the surface, but varnish and microdeposits will disrupt atomization. Ultrasonic cleaning is ideal here, but a solvent bath and careful blowout with compressed air or even small picks and a little bit of drill filing works if you're patient. Once clean, we reinstalled and cross-checked the jet sizes, and we found that they were generally stock for the carburetors, so they were probably perfect for this initial calibration.
So I'm holding one of the air bleed needles for each of these carburetors. I'm trying to balance the airflow on each. But while I'm doing it, I can only get so much adjustment. And basically just these jam nuts are caught up on the threads. So I got to pull each one out, clean the threads up, get these moving again. You can see here, kind of gets stuck. But I can go this way. Basically just got to pull them all out, clean the threads up, put them all back in, and then readjust the airflow. Do it 12 times.
But then comes the sink. With 6 carbs, you basically have 2 schools of thought. Manifold-based or individual throat vacuum sink. Manifold-based measures the total vacuum and equalizes the primaries. For precision, vacuum gauges on each throat are king. Keller opted for individual throat gauges for the final tuning. Tedious? Absolutely. Accurate? Even more so. After syncing, adjusting the floats, and checking the acceleration pumps, almost all of the popping disappeared. Mid-throttle hesitation under load improved dramatically, but it wasn't gone entirely. But that told us the fuel side was now behaving much better, but the remaining issues probably still had an ignition or electrical flavor lurking under the surface. The practical takeaway is always use new intake gaskets, and any downstream air leak can ruin a sink reading. After changing fuel pressure, always recheck float levels. Changed feed changes how much the float settles. And don't rush sinking carbs. Work them symmetrically, left, right, then refine together. The end result ran smoother. Tip-in popping, basically gone. Mid-throttle response, much improved. But the fuel system is now honest and predictable, but that's the platform we needed before moving on to anything else, including the electronic ignition troubleshooting, which we found out we needed. This is the part that people usually underestimate. Mechanical distributors and old school ignition modules seem simple until they decide not to be. On our pickup run, the car would idle just fine, and then suddenly nothing. Dead spark. Sometimes it would come back a second later. Sometimes the voltage would dip, and these are basically classic signs of an ignition module folding under thermal or electrical stress. Digging into the hardware, this LMO2 was running a GM-style HEI module. Now, HEIs are built for V8s, 8 firing events per cycle, meaning that our V12 had 50% more events per unit of time at any given RPM. So, the same firing order, the same net RPM, but more sparks to push through the system. More cycles mean more heat, more current, more stress. Stick a V8 HEI on a V12 without protection and expect it to fail sooner rather than later.
All right, so we ran into an issue on this LMO2 that basically just testing it out, sitting here idling, the car instantly died. Checked a few things, basically doesn't have spark. Traced it down to the ignition control module, which is this piece sat right here in the fender. And turns out they use some older GM style high energy ignition module. But I think it died because typically it's going to be mounted inside your distributor, and the distributor can soak up all the heat that this thing makes. Although you get some heat from the engine, but basically with this 3D printed cover just sat on here. So I feel like this part got so hot, basically melted itself.
So what do? Well, first, don't assume a failing module is just a bad batch. You got to look at the math. More cylinders, more stress, so protect what you have. Heat, vibration, coil return currents, all of it matter. Heat sinks, airflow, and careful routing keep the module as comfortable as possible, and if you want real robustness, consider splitting the load. Dual small modules or a distributor coil per cylinder setup beats trying to force a single V8 box to handle V12's appetite. However, on this one, without trying to complicate things too much, it really wasn't an option.
So, I put a new one in there, fired right back up. But to prevent it from failing, I'm gonna build a little heatsink box for it. And I'll show you guys that down here. All right, so to prevent this thing from getting too hot, got this little heatsink box here. It kind of just will slide together once I get all the wires sorted, but it's gonna look like that and pull together. But got the new module here, got it mounted up with some heat transfer paste or heatsink compound. Got a little heatsink on top here. It's going to have a fan on it. Got the wires running into this box. And basically this box will just absorb the heat and the fans will push it out. And hopefully this module will have a very long life. Got that there. This fan will go here. Little computer fan in there. Hopefully it stands up to the vibrations of a car, but that's the idea.
We also kept an eye on charge voltage during these failures. Now, a sagging voltage while cranking or idling will make electronics unhappy, and sure enough, that led us into the alternator puzzle you will hear about in a little bit. But fix the fundamentals here and the rest of the system should behave. Now, timing is where headaches can live, especially on engines converted from marine to automotive. And of course, the original timing marks were gone. Why? The marine flywheel and its marks have been swapped out for an automatic transmission adapter, leaving zero documentation for base timing. Now, we could have pulled the engine and tried to restore the flywheel marks, but that's expensive, risky, and full of unknowns. Instead, we went old school. Plug and dowel to find top dead center, scribed a durable reference on the balancer, and used a degree wheel as our crank angle proxy. From there, we set to a conservative 14 degrees before top dead center at idle, a safe starting point for a big naturally aspirated marine V12 running pump gas. It keeps detonation risk low while letting the engine behave predictably. But once we fired it up, we measured total advance under load and at higher RPM, and it was about 27 degrees. Not a hard target, just where the curve naturally leads with the distributor. It's reasonable and safe for now, but more advance could unlock more power later on, but it wasn't about wringing out every last horsepower. The goal here is getting it running and driving clean first. So we fine-tuned the timing using vacuum feedback, plug color checks, and how the car felt on the road. Idle vacuum is kind of the ultimate truth here. The timing that produces the highest steady vacuum without hunting is usually the sweet spot. Now, small measured tweaks while monitoring for heat or knock got us to a stable, predictable setup, that 14 degrees. So why don't we just slap in a MSD box or twin distributors? Well, because that adds triggers, new curves, packaging headaches, and a bunch of potential failure points. So we kept it simple and surgical. Wanted to stabilize the ignition with the hardware that was already on the car, protect it from heat, and only think about bigger changes once the drivability and the repeatability were locked in. And just when you think we're making progress, we notice the once dead ignition system is now working but weak. Spark is faltering, the electronics are freaking out, and the car is giving us that I'm about to quit vibe. And it turns out this LM002 came to us with a 64 amp tractor alternator, wired like it was still on a farm. Honestly, I'm not sure why this was chosen, maybe the simplicity, but here we are, 12 cylinders with a heavy ignition load at low RPM. Basically, everything needed more oomph. We checked voltage under 13 volts at idle, and that's not enough. But if you hit 2,000 RPM, suddenly it's better, but still underfed. So yeah, this alternator is producing, but only once it's spinning fast enough, and spoiler alert, it's not helpful when you're sitting in traffic. So our first thought is maybe we just need more amps. So after far too much time spent looking, I find a 104 amp 1991 Ford truck alternator that was also used in tractors. Bigger rotor, bigger stator, more continuous output, and a sweet bonus, it bolted right up.
What's up, guys? Welcome back to the Lamborghini truck. So I thought I had this thing all set. Testing it out after about 45 minutes, this thing started to die out. Found I had barely any voltage left in the battery. Checking it with the meter, running, it would jump from 13, sometimes below 13, it would jump up to 17, back to 13, back to below. So, figured something went wrong in the alternator. Probably couldn't keep up with all these new electronic accessories, all the fans, electric water pump, high output ignition. So we're gonna swap it out for a new one. Got a new Bosch unit, 95 amps instead of 65, so hopefully that'll take care of everything. This is a new one about to go in. The case is the same, the terminals are in a little different spot. So I had to change one of the terminals and it's hitting one of the heat shields now. This goes around the oil pressure sensor and the coolant sensor. So I had to cut that back a little bit to make room for this terminal here. But hopefully this gets in and that's the last issue.
So problem solved. Not yet. Even with the 104 amp alternator, idle voltage was still weak, and that's when we realized the real culprit. The pulley wasn't spinning the alternator fast enough, too slow at idle. Capacity wasn't the issue, it was RPM.
Kind of sucks. Charging voltage is too low when it's idling. Maybe I'll just never idle the car. Just means we're not done yet.
That, my friend, dragged us into one of the biggest alternator pulley black holes that I've recently been in.
Okay, even after getting this new higher output alternator installed, it's still not charging the way I'd like to at idle. It did bump up the charging voltage when you give it a little bit of RPM. However, I don't want to have to be worrying about this thing every time you come to a stop. You know, it's got a lot of draws on it now. It's got the electric fans, electric water pump. And I don't want to have to be worried about this when you're idling. So, easiest way is just make it spin faster, right? So, looking at the belt, we can either change the crank pulley or the alternator pulley. Alternator pulley is obviously easier to change out. So we got this new one here. This one's a 2.5 inch. The original one's about 2 7/8. Smaller pulley means it'll be spinning faster. So I'm gonna get this mounted up. Hopefully this will fix our issue at idle. Just like that. Get it all screwed together, get it back on the car, and let's test it again.
Solution: smaller alternator pulley versus the crank. Spins faster at idle. We double check the belt tension, no slip, no drama, boom. Idle voltage is now stable at 14 volts, steady across the full RPM range, and most of the electronics are happy, coils are happy, car's running predictably. Lesson learned: don't automatically blame the alternator, especially when you're dealing with this sort of custom stuff. It could just be a pulley problem, and for any modern ignition system, stable 14 volts at idle isn't optional, it's survival. Nail that and your electronics will stop making problems. All right, let's wrap this up. What we did here is classic FMU fundamentals under extreme scarcity. No Google results, no dealer notes, no forum posts, just a 6-carb V12 in a Lamborghini SUV behaving like it had a personal vendetta against every diagnostic tool in the shop. We chased fuel pressure swings, synced 6 unforgiving Webers, nursed a heat-stressed ignition module back to life, and figured out timing with nothing more than a wooden dowel and a vacuum gauge. And got the charging system behaving like it was supposed to, all without swapping in a different ignition system or hunting for some mythical spare distributor. Were there compromises? Sure. Timing is conservative, ignition architecture isn't state of the art. Pulley ratios and old school alternators demanded a bit of creative problem solving, but the goal wasn't maximal dyno numbers. It was reliable, safe, predictable drivability, and that's exactly what we accomplished. The bigger lesson here is modern builds chase complexity and electronic sophistication, thinking parts alone equals drivability. And I mean, that's kind of how this thing ended up with us. Meanwhile, fundamentals, air, fuel, spark, and measured logic will always outperform hype when the chips are down. Here's the practical takeaway. Fix fuel pressure first or everything will act unpredictably. Get the carbs in sync and clean, and 6 Webers won't lie. Stress test the ignition modules if you're running a V8 style HEI and a V12. Timing, no marks. Find top dead center, use your tools, road test, and you're done. Charging system, a stable 14 volts at idle isn't optional, it's survival. Now, if you ever find yourself in a no info scenario, remember this. Fundamentals talk back. Measure, change one thing at a time. Before you swap parts, think. That's how you fix a 6-carb monodistributor marine Lamborghini V12 and your own car at home. Now, if this car calls us back for round 2, we could dive into final optimizations, more ignition advance, fine jetting, maybe even twin distributors, or a multi-spark ignition to really unleash the rest of this bull. But honestly, I'm hoping that's a long way off. We've burned enough brain power chasing dead ends and guesswork that we couldn't charge for, and the monetization will never cover it. So let's hope we don't see this thing again until the owner has some real behind the wheel time. Now to get philosophical. Sure, a build like this is kind of about showing off, but you can't get here first without understanding how a machine works, reacts, and coaxing it to perform reliably with your hands and your head. Beauty is in solving the impossible with fundamentals and stubborn creativity. Drop a comment on the strangest ghosted DIY repair you've chased. Entertain us. Schadenfreude, welcome. Stay loud, stay fundamental, and catch you on the next build.